Our speaker today is Prem Devambu. Prem is a professor of computer science at UC Davis. He got his PhD from Rutgers in 1994, worked at Bell Labs for 18 years, and has been with UC Davis for last 10 years.
Thank you for inviting me to speak here about our work. So this is a project we have going on at UC Davis on open source software, development of open source software, studying various aspects of it. It's funded by the National Science Foundation with the Science of Design grant. There's one of the fun things about this project is that it's a very multidisciplinary project. There's people from computer science, notably my colleague Vladimir Filkov, who's a bio-informatician, a whole lot of students. This particular work I'm going to be talking about mostly is the work of two students, Zach Saul, who's here, and Chris Bird, who's not here. So it's mostly their work. The team also includes people from the School of Business, because one of the things we're interested in is to understand how social and organizational structure in open source projects play out and how that interacts with the software design structure. So we have a couple of people from the School of Business. We also have a couple of physicists, Suman Roy and Vladimir and Raisa de Souza, who are interested in the physics of large networks. Okay, so just to quickly summarize the kind of problems we're interested in, large software projects are always of great interest to software engineers. So you have large teams of people building these really complicated artifacts. Shown here as some kind of complicated graph with many different types of nodes and dependency edges. And these go to users, and the users are generally not happy because there are lots of bugs, and it's everybody hates it. And there's lots of problems that come along with large software systems. Instantly, when I gave this talk first in Switzerland, my audience told me that I got the ethnicities of the developers and the users reversed. So, so there's lots of problems. So it's one aspect of the problem is the size and the complexity of software systems and the need for constant change. Another problem is what we call discovery, which is that the systems are so complex and so many dependencies involved in there that it's hard for people to even learn about how it's built and to work with it. People invariably make mistakes and introduce lots of bugs, and the users get unhappy. So software engineers have been wanting to study this for a long time, but it's been difficult, mainly because when you're in a university, an academic environment, it's hard to get data to study what are the factors that actually drive this and create the real problems. So maybe you could try to improve upon them. So open source projects are like special in this sense. They have all the problems that you see in traditional closed source projects. So you have, for example, a lot of communication and coordination going on in open source projects, which is affected by the distributed aspect of it. And a lot of this data is actually available. You can see how people talk to each other, how they work with each other, and so on. In this sense, the interesting thing is that the design of the system itself can help or hinder with the way people and teams work with each other. So if you have a system that's well organized, maybe you're better able to divide it among teams and have the teams work with each other better and have less need for coordination activities. So design can be either a hindrance or a help. So there's this thing called Conway's law due to Lynn Conway, which says that essentially that artifact structure and organization structure kind of mirror each other over time. So this is actually the core of our project, our Science of Design project, which is to study the relationship between design and social structure. Another thing that's interesting is that in every software project, one of the key aspects is bringing new people in and bringing them up to speed. So invariably, this takes a lot of time, and new people, invariably slow everybody else down. So this is kind of also dealt with in Brooks's law. Some of you might have heard this book called The Mythical Man Month. And Brooks's law basically says that adding new people to a software project that's already late makes it even later, right? So adding new people is a crucial issue and something that's really worthy of study. And this is one of the things, first things we did was to study how new people joined open source projects. And for open source projects, there's another aspect to it, which is that if you don't attract new people, eventually you're going to die. And also, for many developers, being accepted as a committer into an open source project is a real kind of badge of honor, right? So a lot of people want to become, say, an Apache developer or get commit privileges into certain aspects of Linux. And so understanding this process, how this works, is really, really kind of interesting and important. So this is something else that one can study in open source projects. The other thing that's interesting is the effect of tenure. So this is well known in traditional organizations and has been studied by organizational behaviorists, is that people who stick around in one job for a long time within one organization invariably not only become less productive themselves, they also get in other people's way and hinder other people from becoming productive, because they're sort of like, interested in getting some kind of recognition for what they've already done, so they might resist change or innovation. So this is something else that one can study in open source projects, and we actually have a proposal out to the NSF to study the effect of tenure in open source projects. Okay, so the thing about open source projects is that a lot of the data is available. So they are complicated. They are just as complicated as closed source projects, but all the activities that people have performed is already archived, and you can go off and mine it and study it. There's lots of large distributed teams, but the cool thing is that community norms in open source projects require that all the communication takes place on these archived media, like email lists, right? So it's all archived, and you can go off and study how people interact on these mailing lists, and that allows you a kind of gives you kind of historical record that's just simply not available in a traditional environment where somebody can just go next door and talk to their colleague. But in open source, all this is comprehensive and it's archived. Lots of bugs. Bugzilla has lots of information, and that also is quite useful to figure out the aspects of history that might indicate the presence of bugs or predict the presence of bugs, or predict which bugs take a long time to fix, and so on. So all this can also be studied. So open source, essentially, I mean, the way I like to describe it is that open source has put software engineering where bioinformatics was like 10, 15 years ago, right? So all of a sudden, we have this, like bioinformatics really came to life when people invented gene sequencers and affymetrix chips, which gave you a lot of this data. So now software engineering is now in the same boat. We have like tons of data. And it's sort of embarrassing to me as a software engineer that we're just starting to learn how to deal with this massive volume of data, how to analyze it, how to analyze large dimensional, sparse, time series matrices and learn something useful from it. We're just sort of starting to learn how to do it. So we do a bunch of different things, but I'll basically talk about, probably mostly about one thing, but I might get to the second topic as well. So one of the things we're interested in is developing software engineering tools to help programmers deal with the problems of large software systems, like complexity and scale. The nice thing is, once we develop the tools, we can use open source software itself as a way of evaluating the performance of the tool. Let me show you an example of a tool we built and how we evaluated it. So the tool I'll talk about is a recommender system called Fran. The second thing that's interesting is to study how social activity, technical activity, and design structure all interact with each other. Using open source mailing list archives and CVS archives as a means of studying what people do and how they talk about it. So we've done a bunch of studies along these lines. The thing I'll talk about, if I have time to get to that, is immigration, how people go from being mailing list participants to actually becoming committers in an open source project, and what factors drive this. One of the interesting things we looked at recently in this study of mailing list activity is we looked at how often function names, file names, method names, exception names are mentioned in the email, and how often they're mentioned in commits. So in other words, how often the function names and so on are used in code that gets added, and how often it's actually mentioned in the email discussions. So we were careful enough to filter out patches and things like that from the mailing list. We really only looked at when they're actually talked about. And there's some very peculiar things we found. I mean, it's very new work, so I don't have any slides on it, but we found that cumulatively, the relative frequency of mentions in emails and the mentions in source code is incredibly strongly correlated. But periodically, in terms of monthly, it's not. We don't really quite understand why, but we have some, this is a kind of interesting phenomena that one observes and that we want to study. Okay. All right, the first thing I want to talk about is Fran. All right, so Fran is a recommender system, and I'll explain what that is and why we need something like that. All right, so let's suppose that we have a new developer, Daria, who's writing multi-threaded code for Apache. And she is interested in using multi-threaded, whoops, sorry. She's interested in allocating a shared memory pool to share between threads. So she allocates this memory pool. And then when she's done with the thread, she forks a thread and she runs some code in the thread. And when she finishes the thread, she calls this method, APR thread exit, to exit the thread. Now this APR underbar, if any of you have looked at Apache code, is the Apache portability runtime. It's a collection of about 300 odd functions in about 30 modules that implement various portability functions and makes it easy to port Apache from one operating system to another. So APR has several different submodules, and this one is the thread module, and she calls the APR thread exit function to exit from the thread. Okay, so fine. Now, when she does this, she gets a crash, right? And such crashes are arising here because of APR thread exit behind the scenes deallocates the memory pool. So that's why the system crashed, because the memory pool got deallocated, got used in some other thread for some other purpose, data gets corrupted, and she gets a crash. Okay, so such crashes are going to be like fairly random. They're going to occur at random intervals because they depend on the thread overlapping, the thread interleaving, in order to trigger a particular defect, right? So these are like really hard to reproduce and debug. Okay. Now, if Daria had a recommender system, right, what she would do is she would say, I'm going to call this function and ask for recommendations. All right. Now, this could be built into a development environment, or it could be a tool that she uses offline. But in any case, it might, for example, one possible embodiment is as soon as she types in APR thread exit into her code, pops up a list of relevant functions that other functions that she might be interested in. So if you give APR thread exit to Fran as a query, it returns these functions. Okay, these are relevant functions very closely relevant to APR thread exit that are returned by this recommender system Fran. Okay, so once Daria sees these functions, she can then be prompted to go off and look at these other functions, and she'll quickly realize that a side effect of APR thread exit is that it'll call a flushing of any pool that was allocated. So by knowing this, then Daria can essentially avoid this kind of coding, which might lead her to introduce a bug that's very, very hard to debug. Okay, so that's the goal of Fran. Given a function, find related functions. It's a very, very simple goal. Okay, and so this is an active area of research right now. There was recently the second workshop on recommender systems I just attended a couple of weeks ago, and there's almost in every software ICSI or FSC software engineering conferences there's some papers on recommender systems. Netflix prize has given a big boost to the whole area of recommender systems. So this is essentially the same kind of problem, finding relevant functions. Okay, all right. So assuming the problem is clear, I'll press on. Okay, so given a function, return a set of functions. Okay. So that's the problem. Now, there's lots of different ways that recommender systems can work. One of the ways recommender systems can work is to use versioned code. So they can look at like 100 versions of the code and say, whenever somebody added a function call to this function, they also added a function call to this other function. That's one way in which recommender systems have been built to work. So we're sort of giving ourselves a harder problem. We're saying we use only one version of the code. Don't use multiple versions. So what does Fran do? So Fran essentially kind of works by sort of imitating the behavior of a programmer, right? So a programmer, when they're looking at a function and trying to find relevant code, they might look at the body of the function that implements the function they're interested in using. So they might look at the body and say, what are the functions does this one call? Or they might look and see, what are the functions called the function I'm interested in using, and what functions do those functions call? So it's sort of a neighborhood. Given a function, there are other functions that call this function and the ones that are called by the ones that call this. And likewise, you take the ones this one calls, the other ones that call those. So there's a whole neighborhood of functions, right? So essentially, programmers would explore this neighborhood looking for related functions. So in a sense, Fran is doing the same sort of thing, right? So it does some kind of random walk of that neighborhood and returns the functions with the highest probability of being visited. Okay, and it works actually really well. It's a very, very simple algorithm, but it seems to work extremely well. And we'll show you how we evaluated it. Okay, so step one, select a neighborhood of the query function. So this is how we select the neighborhood. So assuming that this is the query function, we assume a single query function that you're interested in. Right? These are the functions called by this query function. And these are the other functions that call the functions called by the query function. So these are called spouses. So for example, if this is some APR thread exit, what are the other functions that call APR thread exit? And those are called the spouses. Likewise, you also look at the parents. These are the functions that call the query function. You look at the other functions called by the parent function. So this is your complete neighborhood. Okay, so this is the neighborhood we use. Okay, and now what we do is rank the functions in the neighborhood. Sometimes these neighborhoods can get quite big. We sort of, in somewhere like in the 300 odd range, we sort of cut it off. But they can get very big, right? So we sort of prune the neighborhood beyond a certain size. And then we rank them, okay? And usually we return the top 5 or top 10 or top 15 functions based on the ranking. Okay, so how does ranking work? So Fran uses two concepts called sourceness and targetness. So sources are functions in the neighborhood that call a lot of functions in the neighborhood. So what we're trying to do is to find functions in the neighborhood that are most specific and most like the function we're looking at. Okay, so we say, okay, there are functions that are in the neighborhood and functions that are not in the neighborhood, right? So we'll take the functions and see what are the functions called by a lot of functions in the neighborhood, right? These functions are source-like. And likewise, there's a notion of targetness, which are functions in the neighborhood that are called by a lot of other functions in the neighborhood. So there's a notion of sourceness and targetness, and sort of a mutually recursive definition. Okay, and what we claim is that targetness, which are functions that are called by a lot of functions in the neighborhood, it determines how relevant a function is. So what we can essentially do then is define sourceness and targetness vectors. So these are vectors with the same dimension as the neighborhood. So every point, every function in the neighborhood is a sourceness score and a targetness score. Okay, and so we have these sourceness and targetness vectors, S and T. Okay, and we start with an initial source score vector S0. Okay, and we have the connectivity matrix for the neighborhood A. Okay, so and the transpose of the connectivity matrix is A transpose. Okay, so now what you do is you take the sourceness score. Okay, and from the source you apply the transpose of the connectivity matrix. This tells you essentially, if you apply this, it essentially tells you how likely you are to get to a particular target based on the source. Okay, so this gives you the targetness scores based on the connectivity of the call graph and the sourceness scores. So if you call from more sources, then that particular entry in the targetness vector will be higher because you'll have more ways of getting to the targetness vector from this matrix. So that the matrix has more non-zero entries in the columns, then the corresponding targetness score for that entry will be higher, right? So it essentially reinforces targetness based on source. And then you have the next step, which is the dual of it. So likewise, you take the targetness scores and you multiply it by the connectivity matrix. And likewise, if something is called from many sources, then that source will have higher sourceness score, right? So then you can simplify it and get this kind of iteration. Okay. So once you've got this, then you get the convergence property from Kleinberg. So essentially, S and Ti are Markov chains with probabilities built from A transpose A and A transpose. So the result due to Kleinberg is that Ti converges to the principal eigenvector of A transpose A. Okay, and S converges to the principal eigenvector of A transpose. Okay, and the paper is in Siam Soda 1990. So this was essentially actually one of the ideas of how to do page ranks, which came about before the famous page rank paper. So this is one of the earlier formulations of using links to calculate ranks. So here instead of links, of course, we're using the call graph. So it's a similar idea. Okay, so you construct the neighborhood of the call graph or the neighborhood graph of the query function. You construct the edge incidence matrices A transpose in A, and you find the principal eigenvector. The largest values of the eigenvector gives you the most relevant function. Okay, so given a query function, you construct the neighborhood of the query function, you construct these matrices, and you compute the principal eigenvector of A transpose A, and that gives you the scores. okay, relevance scores. Okay, so the question is, so there's been a bunch of other ways to do recommender systems before this work was done. So the question is whether this actually does better than existing work. Okay. All right. So the two previous approaches that used call graphs to compute relevance scores. One is based on data mining, association rule mining, essentially, and the other was a system called Suede. Okay. So data mining. So data mining essentially is a frequent item set mining. So that says that if two functions are called together more often, then the two functions are more related, right? So if two functions f and g are frequently called together, then f and g are very closely related to each other, right? So it's basically that idea. So what you do essentially is, given a query function, find all the functions from which it is called. So what are all the functions that call the query function? And find the other functions that are co-called in those functions, along with f, right? And then you return them using the most frequently co-called first, right? So if f and g are co-called with each other 10 times, and f and h are only co-called 9 times, then g will be higher ranked than h, right? So there's a bunch of papers that have used this approach. One was in ICSI 2000, the other was in the Software Repository Mining Workshop a couple of years ago. And so this is one thing that we compared our work with. The other algorithm that does this sort of thing is called Suede. So Suede essentially uses any kind of relationship and any kind of entity to find relevant functions. And it uses two properties called specificity and reinforcement, which is actually very closely related to targets and sources, as you'll see in a second. So essentially, Suede works with a set of query functions, a set of functions used as a query in a relationship. So Suede says that given a query, functions that relate to few other functions besides the functions in the query are specific, right? And functions that relate to more functions in this query are more reinforced, right? So if you have a set of 4 functions, you look at those functions that are related to as many of the 4 as possible, and they're related to very few others besides the 4 that you've used in the query set, right? So there's a function that is called by the 4 functions in the query set and not really called from anywhere else. That's very specific because it's only called from functions in the query set, and it's highly reinforced because it's called from all the functions in the query set. So they look for both these properties, specificity and reinforcement. Okay, and it returns the ones that are most specific and most reinforced. Okay, so the way Suede works is similar to considering a smaller neighborhood than what Fran does, and it doesn't do any kind of iteration. So the ranking in Suede is not as good as the ranking that we do. It considers a smaller neighborhood, and it doesn't rank them as well as we do. Okay, so we did a comparison of these two things with our approach. Now, one of the sort of key controversies in recommender systems is how do you evaluate them, right? So given a recommender system that finds related functions, how do you evaluate them? So I can sort of like quickly review some of the different things that people have done with the recommender systems. So for example, one thing is recommend somebody who will fix this bug, right? So given a bug, recommend somebody who will fix this bug. And the ways people have done it is by essentially using historical data, right? So what they do is they'll train the system based on the history of bug fixes in Bugzilla until, say 2005, and then they'll take a new bug, the next bug that comes along, say in 2006, and say, I'll take the same algorithm and recommend who's going to fix this bug, and look in the history of this bug later on and see whether the people who actually were recommended as fixers for this bug were the ones that actually did fix the bug. So they use this as a way of evaluating it. This can be done kind of, more or less quantitative automated fashion, and you can have rigorous statistical evaluations in this way. Another kind of thing is like, what we're doing, for instance, is I'm working on a function, which other function is most relevant to it, or which document is the most relevant to it. Okay. In such situations, there is a complication, which is that what is relevant depends on the task that the human is doing, right? So really, the only way to ultimately evaluate whether a recommender system is doing the right thing is to take a human and ask them, do this task. Now, here's my recommendation for this task. Do you like this answer or not? And the human says yes, then it's relevant. If they say no, it's not. Okay. So for this kind of particular recommended task, in some sense, to evaluate systems and to compare them, you really have to have a human subject study. We didn't want to do that, so we chose a kind of we defined a particular kind of task for a recommender system, which we could evaluate quantitatively, and we did that, right? So I'll tell you the task that we chose to evaluate it on and evaluate it. So we essentially wanted to judge which of the three algorithms was better, right? So imagine doing this with a human study, right? You have to essentially have several different, you have to a combinatorial study where you have several different control groups which are matched with each other in skills and expertise, and you have to like sort of give them similar tasks and have them compare the value of the recommender system. So it's very hard to do comparative studies with human subjects. So that's one thing we want to do, whether the algorithm is better. We want to know if any of these algorithms are actually better than random guessing, right? So we want to do that too. The other thing we'd like to do is, although our results on this I think are tentative, we'd like to know, is it possible to predict when one particular algorithm is going to do better than the other on a particular task? And if you could tell when one algorithm is going to do better, then you can take the different algorithms and decide which one to use and use that one for different settings, right? So if you know that under these conditions, this recommender system is going to do a better job, then you first look at the problem for which you want a recommendation and say, okay, for recommending horror movies, this algorithm is better, so I'm going to use this one, right? So you could do that. So we did that in this case, and we got some interesting results, but probably you want to take it with a pinch of salt. Okay, so all these things are kind of really hard to do with human subject studies. It just gets very expensive and complicated, and there's lots of threats to the validity of any experiment that you do because of variability in human subjects. So it gets very expensive and difficult. We didn't do that. So what we did was we defined a particular notion of relevance, right? Particular notion of relevance which we could automatically have kind of an oracle for, and we evaluated the recommended tools based on this oracle. So we used the Apache portability layer for finding relevant functions. So we needed a set of answers that will tell you, given a query, what's the right answer, right? So this is what we did, okay? So the Apache portability layer has 330 functions. The functions are grouped into 32 modules. And the problem we set was, okay, we're going to take each module and use each function in the module as a query. Given the function in the module, the recommender system should return other functions in the same module. So that's a task we set. Okay, now, is this a relevant task for the recommender system? In the case of Apache, no, because the document already tells you what the functions in the modules are, right? But remember, we're not using the documentation. We're just using the call graph, right? So essentially what we're doing is we're using the call graph to reconstruct the modules, right? In some sense, this old problem that a lot of people are dealing with a long time ago of taking C programs and converting them into object-oriented programs. They would try to find objects in C programs. This is like a classical challenge in reverse engineering, is to find objects in functional programs. So kind of we're doing that, right? So we're essentially saying, can we just use the call graph, a single snapshot of the call graph, to find modules, okay, without using any other information? Okay, so this is the task we set for ourselves. Okay, so it's a realistic task. We have an automated oracle that tells you what the right answers and not the wrong answers are. And we have a non-trivial sample size. There's 330 questions we can run. So we can get some good statistical data on whether we're doing better than other tools. Okay, the problem is that it's very, very specific task, right? It doesn't really address the vast range of things a programmer might want to do for which they might want to have some recommendations. So it doesn't really address a large set. It addresses a very, very specific problem. And maybe it's a bit over demanding, so we were criticized for this because essentially our problem setting allows you to give one single query function and find related functions. And some of the other tools that we're comparing against don't really work all that well with one single query function. So basically the response to that is we expect that our performance will improve if you have more than one query function, right? So we have to do that experiment, but so that's another possible criticism of the way we do the evaluation. Okay, so the evaluation question stated here as null hypothesis is that the tools don't do it. Given a tool, it doesn't do any better than random guessing. That is, you take the set of functions and you pick them at random, and the tool doesn't do any better than that, right? And the second hypothesis is that the answers we give, in terms of precision and recall, are no better than the other tools, right? So essentially, these are the hypotheses we want to reject. That is that our tool actually is doing better than random guessing, and our tool actually does perform better than the existing tools. And in fact, we do reject them. Precision and recall. So recall is, supposing you have a set of possible answers. Some of them are correct, right? Some of the functions are actually relevant. How many of the correct ones you get. And precision is how many of the ones you get are actually correct.
Yeah.
Right. So they're sort of duals of each other.
Yeah.
And the F1 score is the harmonic mean of precision and recall, which is you take the product and divide by the sum. Twice the product divided by the sum. Okay, so the first null hypothesis is that the top k ranked for query function is no better than random guessing. Okay, and so now when you say random guessing, you have to have some kind of combinatorial model of what a random guess is, right? So it's a very, very simple model, right? So the idea is you basically have, you have your whole set of answers, and some of them are right? And you want to see how many of them you would get if you were guessing at random. So the way we think about it is, let's suppose you have a box with, 1,000 marbles, and let's say some portion of them, 50 of them are black, right? The rest of them are white, right? And the black ones are the right answers, right? And you go in there and you pick 10 of them, 5 of them, 10 of them, 15 of them, right? So if you choose 5 answers at random, what is the likelihood that you'll get all 5 black balls, right? If you pick from an urn that is 1,000 white balls and 50 black balls, and you pick 5 at random, what is the chance that you'll get all the right ones? Pretty low, right? So if you consistently keep trying and you consistently keep getting all black ones, then you're doing much better than random guessing, right? Likewise with 10 and 15, right? So this is a pretty simple combinatorial model. It's called the hypergeometric distribution. It's just basically one C something divided by C something times C something. If you work it out, it's really very simple. So that's basically the random model, what you want to get. So if you're really doing random guessing and you pick a certain 15, let's say you pick 15 balls out of this, the distribution of the black balls out of the 15 will follow a certain kind of symmetric distribution. Basically if you have your proportion of black balls is k%, or say not k%, let's say it's x%, then if you pick 15, then the mean and the mode are going to be around 15 times x, right? You're going to get that many black balls roughly if you pick at random, right? Because you're picking them, without knowing what's in there. And if you get all black balls, it's going to be, chances are you're doing something really good, right? So that's basically the random model. So essentially for each value of k, that is picking 5 answers, 10 answers, 15 answers, you run all 330 queries, right? And what you do is the number of times a tool gives you an answer that is less than 1 chance in 20 of occurring at random, right? So if you get all answers are right, it's very, very low answer. If you get 3 or 4 right answers, it's probably pretty unlikely, but may not be that unlikely. So what we're doing is we're only considering answers that would be likely to have been obtained less than 5% of the time by random chances. So we're rejecting anything below the 0.05 level, above the 0.05 level. Okay, and we correct for multiple hypothesis testing. So essentially what that means is if you buy 330 lottery tickets, you have a pretty good chance of winning at least one, right? So there's a, just purely out of random chance you might get at least some right. So if you're doing 330 experiments repeatedly with the same data, some of them might turn out to be right just by random, right? So you want to correct for that. What that means is that you say, since I'm doing so many tests, the p-value I get should actually be higher because I have a greater chance of getting a right answer by purely random chance, right? So you adjust the p-values upwards because you're doing so many tests. So that reduces the number of cases where you're giving yourself credit for finding an answer that is better than random guessing. Okay, so this is the answers, this is the results we get. So what this tells you is the number of times each algorithm gave you an answer where the number of right answers was less than 5% likely to have been obtained by chance, by pure chance. So in this many cases, with top 5 answers, Fran gave 206 answers where the number of right answers was unlikely to have occurred by pure random chance more than 5% of the time, right? So this tells you that Fran was able to give you right answers these many times, Frad gave you right answers these many times, and Suede gave you right answers these many times. So clearly, we're doing better than random guessing a large portion of the time, right? And we're doing better than the other algorithms. Okay, so this essentially is answering the first question, are we doing better than random guessing? And it appears that Fran is most of the time doing better than random guessing. Okay, Now the next question is, does Fran do better than the other algorithms? All right. So the way we compare that is by using F1 scores. So F1 score essentially does the harmonic mean of precision and recall, and basically it gives you a penalty for doing bad on either, right? So if you're bad on recall or bad on precision, it penalizes you downwards. It's always worse than your precision score or your recall score. Now, why is that? Well, the reason is, right, you can always get your precision up really high by dropping your recall and vice versa, right? Right? Because you can just go off and get more answers, right? Then your recall will go up, but your precision will drop, right? Or you get hardly any answers, and your precision might go up, but your recall will go down, right? So what you really want to do is to not give too much credit for either one and penalize them for doing badly on either, right? So this is computed in a way to penalize the algorithms for considering both. There's some criticisms of this approach, but this is a reasonable way to compare different algorithms. Okay. So what this graph is, the red crosses are Fran, and the blue squares are Suede, and the graph is divided into 3 parts. Okay. So essentially, this is a win for us, the cases where Fran does better than Suede. This is a lose for us, the case where Suede does better than Fran, so we don't do as well as Suede does. And these are the cases where we're tied. Okay. So as you can see, in most of the cases, Fran beats Suede. Okay. The answer, don't get too put off by this. It's just kind of like arranged. The answers are arranged in order to give you this kind of shape there, just to make it easier to read the graph. So you can see that most of the time, Fran beats Suede. Okay. And sometimes Suede beats Fran, but in the cases where we beat Suede, you'll see that Suede actually gives you a 0 value for the F1 score many times, right? It's almost like it's all bottoms out essentially. Whereas the cases where they beat us, we're sort of not quite 0. We're not fairly close to them, right? And then there's some cases where we both kind of don't do very well. Right, so now, this is kind of eyeballing it. You can do a statistical test. So what you do essentially is a statistical test that says that the values of F1 scores obtained from Fran are statistically significantly higher than the values of F1 scores obtained from Suede. And this is a simple kind of t-test, and it's actually a matched t-test because it's in the same queries. You can compare the two. I don't know if that's what we did. We do the matched t-test or the simple t-test? We did the non-parametric version of the t-test, right? So yeah. So essentially, we can reject the null hypothesis that we're not better than Suede. So in fact, we are better than Suede. Okay, so this is comparing Fran with the data mining approach, and the story is similar, although we don't do as much. In the case where we do better than Fryer is not as big a region. We do beat Fryer in more times than Fryer beats us. But we're not as much better than Fryer as we are than Suede. And we match in some of the cases. Again, here also we can reject the null hypothesis that Fran is not better than Suede. So Fran is better than Suede even in this case, even though it's similar. Question? Okay. So we can. Now this does raise an interesting question. Since Fryer does better than us in so many cases, can we figure out exactly when Fryer does better? Right? If there's a simple way of describing when Fryer does better, then we can use Fryer in those cases when it's going to beat us. And then we have a combination algorithm that actually beats both, that does better than both. So we did that. So this graph essentially plots the advantage of our approach over Fryer. When does our approach do better than Fryer? And what we discovered was the initial kind of neighborhood size. If the initial neighborhood is large, then Fryer does better. If the initial neighborhood is smaller, then we do better, then Fran does better. Right? So this essentially tells you that if you construct the neighborhood and if you have a large neighborhood in the beginning, then we're not going to do as well as Fryer. So this gives you sort of a simple way of selecting which algorithm you use. You construct the neighborhood. If the neighborhood is large, you pick Fryer. If the neighborhood is small, you pick Fran. So it sort of tells you a simple way to choose between the two approaches. So that's what we did. And then we have a combined performance figure of the different algorithms. The CAR-B algorithm, the algorithm on top, is combining Fran and Fryer using this idea of picking one when we know it's going to do better. Right? So that gives you better performance than any of the others. Now, this should be taken with a pinch of salt because this might be overfitting, right? So we have this is evaluated in a particular application, which is Apache, for a particular problem, which is recommending related functions in the same module. So it's not clear that this is going to generalize, but we did find that at least in this case, we could combine the different functions and get better performance. We have 10 more minutes? Okay. I think I won't have time to go through the second part of the talk, but I'll try to go through it kind of fast. So this kind of fun project because essentially, it used some very, very old ideas from linear algebra to do this, and we did quantitative evaluation of this approach. Whoops. Okay. All right. Immigration. Now, let me just see what I want to say about this. So I might have to stop kind of halfway through this talk, but I'll just talk a little bit about it. So essentially, immigration open source project, basically the act of immigration is you go from being a mere emailing list participant to having commit privileges. So essentially, what we're doing here is studying what factors influence when somebody makes a transition from being an email participant to being a committer. So it has a lot of uses. It can help OSS project leaders attract new immigrants, identify those people who are more likely to be productive committers, and then bring them in. It can also help people who want to become, say, for example, an Apache developer or a Mozilla developer, help them, give them ideas on what kinds of behaviors, what kinds of actions will help them gain admission into being committerhood. It may also be useful to companies that are interested in supporting open source projects. So, if you're an open source project supporter, you might want to know which projects are vibrant, which projects should be, you should try to support, and how to get your people to influence the direction of the open source project by becoming committers and so on. So this could be quite interesting for a lot of people for a lot of different reasons. So the way this is studied, I might have to stop with a quick comment on this, and I'm happy to tell you more, and there's a paper on this if you're interested in it. This is done using a statistical modeling approach called hazard rate analysis. So what hazard rate analysis does is it essentially studies the rates of transition as a function of different predictors. So a classic use of this is cancer survival, right? So you have people who have cancer and you want to know when they're going to die, right? And what you do is you sort of fit in different predictors into the model, like whether they're a smoker or not, or whether they're male or female, or they have heart disease. Another kind of classic use of this is recidivism, right? So you release, release a young white female from prison, and you want to know how likely is it that she's going to end up back in there in 6 months or a year or something like that. So various factors like age and previous history of drug use and so on might be factors that predict when the person's going to end up back in prison. So it considers the rate of transition from being, in our case, from being an email poster to being a committer. So I think I'll leave you with basically this graph, which is kind of typical of all the open source projects we studied. The x-axis is not calendar time, it's time since your first email, right? So number of years since your first email, all right? So this particular graph is for Postgres, but all of them look fairly similar. The y-axis is the rate of conversion. The rate is very, very small, right? So usually only about 1% or 2% of developers in a given period will convert from being an email participant to being a developer, right? So all the hazard rate models essentially work on a population that's at risk and the subpopulation that makes a transition, right? So given, for example, prison recidivism, the population at risk is the number of people that have been released from prison, right? And the x-axis is going to be the number of years since they were released from prison. And the y-axis is the proportion of the population at risk that actually exhibits the recidivism behavior, right? So what we're seeing here essentially, and I'll essentially have to stop with this, is a non-monotonic rate of immigration, right? So the rate of immigration initially is quite low, right? Number of people who convert from being email participants to being developers is quite low. It goes up rapidly, reaches a peak, and then declines, all right? So the paper essentially, won't have time to get into it. The paper essentially talks about the factors that influence the rate of immigration. So we studied essentially 3 factors. We studied demonstrated technical competence, which we modeled by submission of patches, right? We consider social status, which we model by constructing a social network and looking at social network measures, right? And so, and of course, the time since immigration. So we looked at these factors to see which predicts. So the way we explain so the question is, why is it non-monotonic, right? Why does it actually show this non-monotonic aspect? And what we found essentially is that people's level of interest, as exhibited by their level of contribution of patches, which is the most important thing, right? That means you're really engaged in the system and learning enough technical stuff to actually contribute patches. The rate at which you contribute patches drops off dramatically quickly, right? Within about 1 or 2 years, if you haven't yet become a developer, you just stop contributing patches. The same thing happens with emails, right? So if you're an email participant, within about the first 2 or 3 years, if you don't convert to becoming a developer, your level of interest drops very fast, right? So there's a decline with tenure. There's a decline of interest and engagement with tenure. And we believe this is actually true probably even of commercial projects, right? So even in a commercial environment, when you're getting paid for your job, after 1 or 2 years on the job, you're going to get bored and lose interest. We don't have any hard data to support this in software engineering projects, but there's a lot of data to support this in other kinds of companies. So there's a declining level of interest. So that's one trend. The other trend is increasing social status, right? So social status has an enormous impact. Social status we measure using social network measures in the email social network has a huge impact on whether or not you convert into becoming a developer. In fact, the dependence on social network status is exponential, right? So if your social network status increases by 1 unit, we measure it essentially by degree in the social network, the number of people you have connections with. So if your degree increases by 1 unit, your chances of becoming a developer increases exponentially based on that. So that increases exponentially, but social status builds up linearly with time, right? So essentially you have 2 competing trends. One trend is increasing social status with time. The other trend is decreasing interest and commitment with time. So those 2 combined together gives you this non-monotonic property, where the rates increases and then decreases. So there's a paper on this, and if you're interested, there's an early version that's published. There's a fuller version with all the detailed analysis in there that I can make available if anybody's interested. So I think I'll stop with that. Thank you very much. Any questions? Yes.
Just try, just the method descriptions. It's not really what you're using as the metric, but just the descriptions, as well as the callback.
You mean using the comments on the methods as something that feeds into the recommender system? Okay, so there are tools that do that. I mean, so there's a tool called Strathcona where they used LSA, latent semantic analysis, over comments to look for similar functions. We chose not to do that. That's an alternative approach, right? But we didn't do that. I mean, and there's one arguable reason against it, which is the call graph is always there. Comments may not be there, version history might be truncated, but the call graph of the current version of the system is always there, and it never lies. It's always what it is, right? So you can always, if you can get good recommendations based on the call graph, you're always better off. That's right. So so it would be nice if you have some way of combining the evidence from LSA or something like that over text to this. Yes, yeah, it's very true. Right.
How do you discover somebody's social network? How do you build those?
Okay, so the way there's 2 papers on that you can find off our website, but essentially we take the emails a broadcast medium for open source projects. So if I send a mail and you reply to it, there's an indication of information flow from me to you. So essentially you're voting for my email and saying my email is a good email. So my out degree increases when you reply to it, and that's an indication of social status. Yeah. And there's other measures you can take. That's a local measure that only depends on who I talk to. There are more complex measures which will take to account the importance of the people I talk to. So, if I get an email reply from Guido van Rossum, actually that's not very good in Python because he replies to every email. So, but if I get a reply from Ryan Bloom and I'm an Apache, that's an indication that it's more of an indication that I'm important than I get a reply from a random person. So there's other measures in social networks, there's sort of more eigenvector based.
Yeah, I was thinking it sounds the same.
Yeah. So there are several measures of status. For this particular immigration study, we used in-degree. One has to be careful not to use too many measures because then you're confounding it with too many hypotheses at the same time. So we just used the degree as an indication of status. So by the way, in this project we studied Apache, Postgres, Python, and Perl. So and all of them show very similar properties. Any other questions?
Did you evaluate things like the frequency over time of the patches or emails?
Okay.
To see if there's some sort of correlation there between.
So submission of patches has a very strong impact in several projects. So in every project except Postgres, submission of a patch really increases your chances of becoming getting committed privileges. In Postgres, it doesn't. And it was a kind of a puzzle why it's not that way in Postgres. It turns out Postgres is very reluctant to admit new developers. And we actually found an email on the mailing list that said, if you send in so many patches that we're tired of putting your patches in, then we'll make you a developer. Otherwise, we won't give you commit privileges. Don't know why that is, but it's every project has its own kind of culture. So I mean, essentially there's like 3 kinds of open source projects. Right. So there's basically 3 kinds. There's the foundation, which has a written down constitution. There's the community based, which is like Postgres, which doesn't really have a written down constitution, but decisions are made kind of by committee. And then the last one is a monarchy. Python is an example of a monarchy, so where one person controls everything. So we have examples of each kind in our sample set, which is the 4 or 5 projects, and they also showed a similar behavior, except for this one thing I mentioned with patch submissions in Postgres. So.
Something like Eclipse, where there's a strong institutional component, and people probably have other means of communicating with each other besides on the list.
Yes.
They're co-located, so there's a lot of face-to-face contact.
That's a problem. That is a problem.
That'll mess up your data.
That's a problem. Yeah. So so that's actually under discussion right now because one of my students is thinking about doing an internship at Microsoft, and they're sort of interested in this, but their social networks are more ad hoc. People just do face mail, whatever, and you can't really tell what's going on. So many of these projects have community norms that indicate that all substantive discussions related to development must take place on the mailing list, right? Now there's another whole thing which we haven't yet touched, which is IRC archives, right? So we haven't gone there yet, and something else we need to look at. Questions? Thanks.